We know that dry ice goes from a solid to a gas, right? It's almost instantaneous. As soon as you turn your back, it's a solid, right? There you go. You guys can see my screen, right? Because my computer is not functioning at its best lately. So
Yes.
Okay. So as soon as we stick it in solution to kind of warm it up, it forms that nice little vapor. You get that fog-looking thing going on. Why does it do that? Why does it do it so fast? Where like water, it takes time for water to sit there and turn into ice. I mean, from ice to turn into water, right? It takes a little bit of time. What do you think is the difference between that dry ice? Dry ice is carbon dioxide. Water is H2O. What do you think is keeping those things, intact?
So since we're talking about the forces, would it be the forces?
A good answer. Okay, yeah. So it's going to be the molecular forces. Okay, we know that carbon dioxide is a non-polar molecule, right? So we know that it doesn't sit there and make that partial positive and that partial negative charge. We know that it's just carbon dioxide. It has no polarity associated with it, right? So we know that it's being equally pulled on both directions outside. So there's no polarity since they kind of cancel each other out. Okay. So, but water, we know that water has what we call that partial positive and that partial negative. Did Jess tell you this was her favorite chapter? Hi.
Hello.
She loves this chapter, right?
Yeah.
Although you guys had the blue slides of death, so
Oh gosh.
which they will probably end up getting because I haven't had a chance to go through all the material. So.
I'm gonna torture them with those slides.
A little bit, right?
Yeah.
Yeah. Okay. So these guys, water forms a partial positive and a partial negative charge. Because it has a partial positive and a partial negative charge, what happens when you put things that are positive and negative together?
They attract.
They attract. So water molecules are able to sit there and attract with each other, right? So we'll have this other water molecule kicking it over here. It's going to orient itself so that, move it. I should flip this around. Okay, so these partial charges, they're going to be able to interact with each other. They're going to form what we call, like I said earlier, this guy's called a hydrogen bond. It's not really a bond. It's really like a fist bump, right? They're interacting, and the more of these that you have, the more harder it is to sit there and separate. So it's a whole bunch of people making fist bumps. So if we all stood in lines, and this is something that I miss about in class, you could actually do it in class. We all stood in lines, and there's about 10 of us making fist bumps, and somebody was trying to get through, break up those fist bumps. Wouldn't it slow them down a little bit? It would take them a lot of energy to sit there and make it through all of us, right? But if there's just one fist bump, it's really easy to sit there and disrupt it. Okay, so because you have all of these water molecules that are interacting with each other and interacting with each other and interacting with each other, we go from a nice, if we go from the frozen state, from a solid to a liquid to a gas, where carbon dioxide doesn't have any fist bumps, right? There's nothing that's going to be keeping these together other than what we call weak forces, or we would call dipole attractions or dispersion forces. Okay, and I'll talk to you about all of those here in a second. Okay, but I want to talk to you about the hydrogen bond first, because that's the one that we've already been kind of familiar with. We've been kind of talking about it. Now, it's not a true bond, it's more of a force. But we call it a bond because you know, chemists always thought it was, I mean, not chemists, biologists always thought it was a bond. So they said hydrogen bonding. And so we've just kind of, okay, we'll let you call it a bond, but it's not a real bond. Are you with me? Cassie, you have that look. Don't cry yet. Right? Because we know that these guys form what we call dipole moments, right? Dipole, meaning that the electron is going towards the oxygen, right? So that means they do have dipole moments, but it's going evenly, right? Because it's going evenly, nothing is going to be truly positive and negative or partially positive and negative like water is, right? You're going to have a moment, okay? So it's going to be slightly, because we know that it goes like this, but we know that this other oxygen is going to be pulling it back, right? And so it's just going to be kind of fluctuating between the two. So it ends up balancing each other out. Does that make sense? So do you guys, there's an old show called Battlestar Galactica, and there is the robots, and their eyes would go zoom, 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 right? You guys remember that?
Yeah.
Okay, so that's what's happening with the electron, right? So here's carbon, and you have that electron that's going zoom, 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 zoom. So no side is favored more than the other. It's kind of even is out. But you don't really have a truly positive and negative charge. Where in the case of hydrogen and oxygen, in this case, it's clearly pushing towards the oxygen. Both of them are. And so that one you have a clearly, it's a clearly partial positive charge. It's not complete, right? It's not an ionic charge, but it's a partial charge. Does that make sense?
Kind of, yeah.
Okay.
So partial because of the movement?
Yeah, because it's moving and they're sharing, right? They're partial because they're sharing the electron. It's not that the electron is going over there and just, it's like, this is your electron, dude. That's it, right? It's not like an ionic where they get the electron. It's not full, you know, it's not complete.
Okay.
You know, it's like when you partially love somebody, right? You're not gonna sit there and kill yourself over them. You just kind of, you know, they're really cute and, you know, sexy. I just only partially love you, you know. You don't give them your whole heart. Okay? Does that, are you guys getting it? Okay, Alberto. Are you getting it?
Yeah.
Okay, so the other types of forces that we're going to be talking about are dispersionary forces. Dispersionary forces, because let's say we have certain things that don't, best way of describing this, because electrons are moving, and because electrons are moving, you get what we call dispersionary, right? And so what will happen is that these forces will allow things to interact. They'll interact based upon characteristics of the properties. So like, for instance, if we have oils, oils are basically a lot of carbons. You guys remember carbon structure? So there'll be long carbon chains, right? And then they'll have a slightly polar tail, or there'll be a glycerin end to it. And in that case of those long carbon chains, right? Because it's non-polar, those guys are going to want to interact with each other, right? You guys played with oil and water before. So if I put two oils together and then I put them close enough to each other, what will happen to those oils? Will they mix or do they stay separate? Let's say I drop a piece of an oil pellet right here, and I drop one right here. What happens? Okay.
If it's two oils, wouldn't they mix?
They're going to mix, right? They're going to mix because they're both going to be using the fact that they have hydrophobic forces that are associated with it, or what we call dispersionary forces. So that allows them to come together. They're going to interact based upon their similarities, similar properties, and things like that. So those are going to come together. So if I have two oils, right, they're going to mix. But if I have oil and vinegar, what happens?
They separate.
They separate. Why?
Because of the forces.
Good answer. See, when in doubt, because of the forces. Yeah, well, we know that vinegar is just acetic acid, right? So you guys remember what acetic acid looks like?
Kind of.
I love this. Kind of. That's our answer for everything. Kind of.
I'm being honest.
Oh, I appreciate your honesty, you know, but I'm still going to tease you about it, right?
Yeah.
I remember acetate from Saturday,
Well, acetate.
and then
is-
the ick, yeah, the ick, because you add an hydrogen, right?
Yep.
For the, yeah, it was like C2, yeah, H something.
Okay, so this is acetic acid, right? So in the case of acetic acid, we have this hydrogen and this oxygen. So then we're able to sit there and have something that is partially positive and partially negative. And then even here with this carbon here is going to be given up a little bit. So this guy's going to be partially negative, and this guy's going to be partially positive. Okay, so these molecules, the acetic acid is going to sit there and interact with each other based upon what we call the hydrogen bond. So your hydrogens are going to interact with these oxygens, right? To sit there and form that connection, that fist bump. Okay, are you with me?
Yeah.
Okay, so that's an example there, right? Okay, so we have what we call dipole-dipole attraction. This would be hydrogen bonds are basically a special case of dipole-dipole attraction. Dipole-dipole meaning that you have a polar molecule interacting with another polar molecule because it's partially positive and partially negative. Okay, so hydrogen bonds are just a special case of dipole-dipole interactions or attraction. Does that make sense?
Those the
So-
ones that need fluorine, oxygen, and nitrogen with
That
it?
is correct. Yes.
Okay.
So dipole interactions are going to have, you know, they're going to be composed of fluorine, bromine, oxygen, nitrogen. So they're going to be composed of those things because when you put fluorine with, let's say, oxygen, what happens? Is this polar or is this non-polar? And who is favorite? Somebody's in the chat.
Isn't fluorine favored because it's stronger?
That is correct. Fluorine is going to be favored. So that means the electrons are going to be going towards fluorine, right? Remember, fluorine is the little Napoleon. He's abusive and all that stuff. Remember we've talked about that?
Yep.
Okay, so in this case, this guy is partially negative. And then in this case, this guy is going to be partially positive, right? Because the electrons that they share are going to be spending more time with fluorine than they're going to be spending with oxygen. Okay, now this is called the dipole moment, right? So that means it forms a dipole, a positive pole and a negative pole. Okay, so that's why we call it dipole. Di meaning two, poles, positive and negative. Make sense? Okay, so we didn't want to call it bipolar because then we think about bipolar, which would probably make us, you know, a little more sense to us because we think about when somebody's bipolar, they're positive one moment and then the next moment they're negative. I know this from experience because I've dated a lot of women who were bipolar. So, okay, so that's how I always remember it. Okay, are you with me? So if I have two dipoles, they're able to sit there and form a dipole attraction. The positives are going to attract to the negative component, and the negative is going to attract to the positive component. So if I have a solution of these guys, this guy is going to interact with this guy. So you're going to get an interaction. Okay, and I draw the lines, you know how like we draw bonds like this? I draw the interactions like this, so that represents interacting. Okay, does that make sense? So it's not like a real bond, it's an interaction. Okay, do you guys get that? Okay, so I'm going to go to a whiteboard, and then I'm going to go through some of these different interactions so that we can go over all of them, because then we have to get through this chapter pretty quick. And there's technically 106 slides in this slide presentation, but there are key components of it. Maybe lines. Yes.
Can there be more than one intermolecular force present?
What do you think?
We shall ask the class. Can there be?
Yes, right?
The correct answer is yes, because you could have a case where you have a long carbon chain and a polar head, right? So kind of like your biolipid, right? Or your phospholipid, sorry, not biolipid. Your phospholipid. One side is polar, meaning that it has that positive and negative charge on it, and the other side is hydrophobic, meaning that it's just a long chain of carbon. So in that situation, you're going to have dispersionary forces on one side interacting, and then on the other case, you're going to have, excuse me, you're going to have dipole-dipole attraction. Does that make sense?
Mm-hmm.
And I know that like the majority of you guys have already taken biology, right? Okay, so let's see what I have. Let me go to whiteboard real quick. And then I'm going to show you some pictures, kind of help us understand it a little bit better. Okay, so far we've talked about hydrogen bonds. We've talked about dipole-dipole. Okay, so we talked about dispersionary. And I'm going to elaborate a little bit more on dispersionary so it'll be a little bit clearer, if you guys don't mind my ranting. Dispersion forces. Okay, so when we talk about dispersion forces, we have a molecule. And this represents a molecule here. So let's do the carbon and do this. Oops. So do you guys remember the electronegativity of carbon and hydrogen?
Carbon's more electronegative.
Carbon is more electronegative, right? But is it by a lot?
I don't think so, no.
Okay, so we know that carbon is slightly more electronegative than hydrogen. And so if we did the calculations, we would say, oh, it's a non-polar bond because of that. But in reality, what happens is that your electrons are constantly moving, right? So if your electrons are constantly moving between these two, since they're being shared, but it's being shared almost evenly. So at one moment, I'm going to draw the screen. One moment, the electron is going in this direction, right? And then the next moment is going in this direction. And you have it going both ways, right? Because it's going to be circling both of those center atoms, right? Or both of these atoms, right? Circling the nucleus. Okay. Because of that, it's going to be like, okay, so it's going to be like a nice little wave, going back and forth. Kind of like, remember I said, the guy, zoom, 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 right? So by going zoom, 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 zoom between it, it's going to sit there and form what we call a dispersion force, right? So occasionally, real quick, it's going to be positive, and then real quick, it's going to be negative, right? But it's going to be happening so fast that these forces aren't strong enough. They're not maintained long enough to sit there and sit, right? And so, but they exist, okay? So that's what happens in the case of also with carbon dioxide, right? So then what happens here is that because those electrons are constantly going between those, really, it's literally going this direction and then this direction, right? In equal, okay? So then the next carbon dioxide is going to be doing the same thing, right? Now, if this one is going in this direction, right? And then this one is going in that direction, so they're going to be slightly attracted to each other for just that moment until they start going back the other way. But they're still going to have some type of attraction, but it's going to be a weak attraction. Does that make sense?
Yeah.
Okay. So that's essentially what's happening in the case of dispersion forces, right? And so because those electrons are always moving, you're relying on the fact that the electrons are moving, okay? Okay, so another one is, and then again, I'll show you a picture. It'll make a little more sense with the picture because my artistic skills are like a 2-year-old. Another one is called induced dipole. What do you think induced means?
Like you make it happen.
Like I make it happen. Okay.
I'm thinking induction of like a pregnant woman. So that's why I'm like, you make
exactly.
it happen.
Like I make it happen. So in other words, you give it something that's kind of sexy and you're like, hey, come on, bring those electrons towards here, right? So like in the case of if we had like a sodium positive ion, right? So it can induce dipoles because that has a plus charge, right? So then in the case of, let's say, methane, right? So what's going to happen is that the electrons here are going to be induced to go in this direction where that sodium is at. So you're putting that sodium next to it. They say, hey, I got a little legs. So what's going to happen? Those electrons are going to start trying to go to that sodium. They're like, ooh, sodium, Okay, so that's an example of induced dipole. Okay, are you good so far?
Yeah.
Okay, so I should also say dispersionary forces, they're also called London forces. So you guys probably learned them when you were in like middle school. They were called London forces.
The what forces? You were kind of far away from your mic.
London forces, or you also may have heard of them called van der Waals forces. Let me write both of those out.
Oh, for the dispersion?
Yeah.
Okay, that's why okay. I heard the London one.
So, but the problem was like van der Waals was just calling, he was kind of anxious and he called everything his force, right? So there's actually 3 of them. Induced dipole is considered to be a van der Waals force as well too. And so people don't really like using van der Waals forces because he kind of used it very vaguely. Okay. Okay. Okay, so let's see. Trying to think. Okay, so then of course we have ionic So induced dipole, and then we have what we call just an ionic. Ionic interaction. Right? And that's just our charges, right? Plus and minus, plus and minus. And then we could have, in terms of that induced dipole, we could have that induced dipole can be done by, we specify, let me kind of elaborate on this one. I'm rusted here. Let's see, we have what I showed you in the case of ionic induced dipole. And we have dipole induced dipole. Okay. Are you with me so far? Yes, no, maybe? Or did you guys give up?
No, we haven't yet.
You haven't yet. So that means you're partially with me. So you're like partially positive.
Yes.
Okay, so we want to try to get you guys completely positive, right? Okay, so 1, 2, 4, 5. Okay. Okay. Sorry. And actually it would be, let me tell you right, ion induced and dipole induced. Okay. And then you could have induced as well. Now these guys are weaker than the others. Okay, induced. Okay, so induced is just, as I said, dispersionary forces. There you go. Okay, so now I'm going to have you guys use your knowledge here. All right. So who's going to be the strongest?
Or ionics, right?
Okay, so ionic is going to be the strongest. We're going to put these in order in terms of strength. If I could spell. Okay, then
Dipole. Oh, sorry, Matt.
there should also include one more. Hold on. I'm going to have to separate these. Okay, sorry, I got one more. Forgot one more on there. We have ionic or ion dipole. So that's kind of like water and salt and water, right? Na plus, Cl minus, and then you have water that's interacting with both, because remember, water is a home wrecker. So we'll have H here, O here, H here. So and this guy will be interacting with the Cl because these guys are partially positive. This guy is negative. This guy is partially positive. This guy is partially negative. Okay, you guys see that? So these guys are going to interact with each other, and these guys are going to interact with each other, right? So that's why water dissolves. Okay, so that is an ion dipole. Make sense?
Yep.
Okay, so we have, okay, so who do you think is going to be next in line? You guys said the ionic interaction is going to be the first.
Isn't it the dipole?
Dipole-dipole?
Is it the ion induced dipole?
We have ion-induced dipole. Okay, so now remember, the ion-induced dipole is just something that is normally not polar. You're just putting an ion next to it to make it act polar. So do you think that force is going to be stronger than, let's say, an ion dipole or dipole-dipole, where you have things that are constantly partially positive and partially negative, interacting, in this case, interacting with something that's totally positive and something that's totally negative? Which one is going to have the stronger interaction? Let me ask you this. When you put salt in water, right, and we mix it all up and it dissolves, does the salt fall out? Like if I just let it sit there for an hour, does salt just go back, all of a sudden become a solid again?
No.
It doesn't, right? So that's a pretty strong interaction that, between the two, right? So in that case, is this guy. So that's going to be our number 2. Okay. So then our number 3. Now remember, hydrogen bonds. Hydrogen bonds is like what water does to itself. Do you see water? Does water, like we just sit it on the counter, does it all of a sudden just turn into steam?
No.
No. So that there is a pretty strong interaction as well too. Okay. So I'm gonna do that. Oops. Put these all together.
Dr. Henry, I have a question.
Mhm.
For ionic interaction, ion dipole, they're two different things.
Yes. Ionic interaction is positive and a positive. I mean, a positive and a negative interacting with each other, right?
Mhm.
Ionic bond,
Right.
right? Makes sense? An ionic dipole is ion and a dipole, where things are completely. So here, these guys are completely. That's like sodium chloride.
Okay.
It's an ionic bond. It's really, but if you think about it, it's 2 different compounds, right? So we could also do ammonium acetate. Oops. Sorry. Ammonium acetate, which is C2H3O, right?
Oh, I
So
see.
do you see that? So that's an example of ionic, or basically ionic interactions or ionic interactions in general, right? So this represents an ion. That's like sodium and water, right?
Mhm.
Sodium ion and water, okay? Or just our aqueous solutions.
Mhm. Okay.
So do you see the distinction?
Yeah, I see it.
Okay. And so the next one would be dipole-dipole. Dipole-dipole would be, we could say water would be an example, but hydrogen bond is a better example of water, because typically anytime that you have hydrogen, nitrogen, oxygen, or hydrogen interacting with nitrogen and oxygen and chlorine. So those are all considered hydrogen bonds. So if there's a hydrogen in it, it's considered a hydrogen bond. Okay. And so that's an example of dipole-dipole. But when you have, like, let's say sulfur and chloride as Cl3, right? So when these guys are interacting with, sorry, Cl2. Okay, when these guys are interacting with each other, right? So those guys, there's a polar reaction going on, right? So a polar bond that is forming, but that polar bond is not as strong as, let's say, with oxygen and hydrogen, right? So it forms what we call just a dipole-dipole. Okay, so let me see. So, okay, and then we have, can I erase this real quick? And then I'll give you the examples. Oops. Start this guy up for a second while I erase. Okay. Okay. So you with me so far? Okay, so then dipole-dipole would be the next one in line. And so then after that, who do you guys think it's going to be next?
Well, following this, I mean, the ion-induced dipole,
Okay,
because the
Correct.
ion would be,
that charge thing. Yeah, that's going to have a stronger effect, right? And then,
The dipole-induced dipole.
that is correct. And last
The
but
dis
not least, is
Dispersion
induced or dispersionary forces. Yep. These guys. Okay. Okay, so to kind of give you an idea of the energy associated with it, I'm going to write that up here. Oops. Man, I am on a roll with deleting stuff today. Okay, there you go. So, energy-wise, this guy, the ionic interaction, that guy, we know that that's going to have a lot of energy associated with it. I can't remember off the top of my head. I'm good. So, weakest scenario, we're talking about, let's see. And when we talk about this, we're talking about, say, the energy that it takes to dissociate it, right? So it would be like our dissociation energy, right? You guys remember dissociation energy?
You said this is going from strong to weak.
Yes, it's going from strong to weak. Okay, so $800. Yeah, if I can get it right, 800 plus. kilojoules per mole. This guy's going to be from like 40 to, I'm sorry, from 10, 40 to 600 kJ per mole. This guy is going to be about 10 to 40. This guy is going to be about 5 to 25. This guy is going to be 3 to 15. This guy is going to be 2 to 10 kJ per mole. And this guy is going to be really, really weak, 0.05 to 40.
And these were the what?
So this is the energy to dissociate them, right?
Energy
So
dissociation.
yeah, so this is like dissociation of these forces. So like for instance, you guys know you have DNA, right? And you know your DNA is a double helix. And they're interacting by hydrogen bonds, right? So the fact that you have a whole bunch of hydrogen bonds that are interacting causes that the energy to dissociate that to be more. The more you have, the harder it is to sit there and break it, okay? Now, this represents the dissociation of, it can be a single bond in this case, because a lot of this is just looking at not a single bond, but a single interaction, right? So you're dissociating a single interaction. So if you have a whole bunch of interactions of hydrogen bonds, it makes it a lot stronger because that energy is additive, it's cooperative, okay? So remember, like I said, if I have, let's say me and Jessica are forming fist bumps, right? And then Cassie's gonna run through, right? And then so she's not going to use a lot of energy to sit there and break up the bond between me and Jessica. She's going to be able to do it really easily, right? But if it's everybody in the class forming a fist bump and Cassie runs through, then it's going to be harder for Cassie to sit there and make it all the way through. Eventually, she's going to start getting slowed down because she doesn't have enough energy. Does that make sense? Okay, so now if you're using, and a lot of times what happens with compounds, right, is that compounds have characteristics of both, right? They could have some dispersion force characteristics. They could also have some ion induced characteristics, right? And so when you have that solution and stuff, the way that they're going to behave, you're going to have a combination of different forces that are going to be involved in it. And then that can either strengthen or weaken how much energy it takes to dissociate them. Okay, so what is the thing that we know about glue? Give me a characteristic of glue.
You said glute?
Glue, as in glue.
Oh,
Glue.
glue.
White glue that you guys use to make slime.
Sticky.
It's it's sticky. That's right. It is sticky, right? So we know that glue is sticky. Part of glue stickiness is a result of those interactions. And those interactions, if you put it on your hand, what happens? Anybody ever stuck glue on their hands?
Well, I mean, a thin layer gets hard. Like eventually, it's still sticky, but it hardens.
Yes, because it's also It eventually hardens, but it's sticky to your hand, and then it actually forms those connections with your hands. Doesn't it take some effort to get it peeled off?
Yes.
Yes. So because you're using those forces are interacting with the forces in your fingertips, in your skin, right? Does that make sense? Yeah.
Yeah.
Okay. Okay, so are you guys feeling the forces? You got it? You're feeling comfortable with them?
Getting there.
Okay, so let's talk a little bit in terms of how these intermolecular forces are going to be used, how we use them, right? How many of you guys drink water? I mean, drink water. How many of you guys drink soda? Sparkling water or sparkling water?
Yeah, bubble.
Sparkling water, yeah.
Okay, so sparkling water is what makes it sparkling?
Carbonation.
Carbonation. Okay, so carbonation causes it to be sparkling, right? Okay, so in the case of carbonation, excuse me, then it causes the water to sit there and be bubbly, right? And in this case, we're interacting water and carbon dioxide, right? In solution. So carbon dioxide still stays the same. So in this case, we have CO2. And we have water, H2O, right? So we're going to have the interaction between these two molecules. So what interactions are going to be involved in these two molecules?
Well, hydrogen.
So we're gonna have some hydrogen bonding. Is what you're saying? Okay.
Yeah.
So what do we know? So yeah, I guess we could have some. Is it truly going to be hydrogen bonding? Because we know that this guy here is it polar or non-polar? This molecule.
Non-polar. It's equal.
It's equal. So it's non-polar, right? Okay. But as you were saying, we have this guy's going to be. Let me put it in a different color. Use red. This guy's going to be partially negative. This guy's going to be partially positive. So we know that this is a dipole, right? Forming here. Same thing over here. Right? So if we have a dipole, we know that this is going to be a dipole. And we know that this guy is non-polar, but it can it be induced or not?
I would imagine you're gonna make it happen. So
Okay.
yeah.
So that's what's happening here, right? Between water and carbon dioxide, we have what we call a dipole-induced dipole, right? Because what happens is that this guy is partially positive. Well, this guy's going to match up with that carbon to make it partially positive. This guy's going to match up with the oxygen side and make this guy partially negative. So it's going to cause it to be shifted. So that hydrogen is going to interact with that oxygen, right? And then forming that weak interaction that almost acts like a hydrogen bond, but it's going to be a weaker in that case, a weaker one in that case. Does that make sense?
Yeah.
Okay. And then your carbon is going to interact with the oxygen, right? Because it's going to be induced, but that's only going to be a temporary, right? It's going to go back. It's going to shift back, right? Because then it's going to shift to the other side. And then when it shifts to the other side, this hydrogen is going to or one from another water molecule. Does that make sense?
Yeah.
You said no?
I said yeah.
Okay. Okay, so remember that zoom, zoom, zoom. So that's what's happening. It's going zoom, zoom, zoom. When it is induced, it's going to be induced. So those electrons are going to be kind of shifted that way, but it can't hold it because it's not within that same complex, right? That strength isn't completely there. Does that make sense? And so because the oxygens are on both ends, the electrons are being pulled one way, then they're being pulled the other way, then they're pulled one way, and then the other way, and then so they're constantly being pulled in both directions, right? But you can induce it. You can cause it to stay a little bit more over here for a little bit, but then it's going to get pulled back the other way because this guy's going to do the same thing over here. You understand? And so you have it. So in that context, we're able to sit there and put carbon dioxide in water, right? And we get that bubbles. But if we put Mentos into it, what happens?
The surface area is increased and it allows the gas to escape quicker.
That's right. The surface area is increased, so then the gas is able to sit there and escape. Or if we shake it up, what happens?
Same thing.
Same thing, right? So we allow the gas to sit there and escape, and then we get soda everywhere, right? Okay, so here's the question for you. I want you to think about it. Okay, did everybody get this down? Did you save it?
Mm-hmm.
Wait, Dr. Henry, I have a quick question.
Yep.
So you induce when you deal with like molecules that are nonpolar, like the carbon dioxide?
Yes. Yeah.
Oh, okay.
Yeah. So because otherwise they're already charged, you know? So if it's polar, you have what we call partial charges, right? So,
Yeah.
so the only time that you induce is when it's a nonpolar molecule. That's a good question. Very good question.
Oh, okay.
Okay.
All
Does that
right.
make sense?
Yes, that makes much more sense.
Okay. Okay. So here's your question. Whoops, wrong question. Okay, solubility is solubility, how much of something can go into something, right? So that would be solubility. So when molecules are soluble in something, it's how much of those molecules are able to go into the other molecule, okay? So oxygen solubility in water is 3.2 milliliters per 100 milliliters of water. And then carbon dioxide solubility is 81.0 milliliters of 100 milliliters of water. Explain the difference between the solubility of oxygen gas and carbon dioxide.
Forces.
I love it. That's correct. It's forces, but give me a little more to it than that. Which forces are going to be involved? If we look at water, of oxygen. Can you guys see my screen? Or did it freeze? So we know that oxygen is like this, right? Is it polar or non-polar?
Non-polar?
Non-polar.
It's non-polar, right? So we know that this guy is non-polar, okay? Now we have carbon dioxide, which is like this. Very similar. Why? Why is it that carbon dioxide is more soluble in water than oxygen? This is why we don't have oxygenated water too often. It has to be done at an oxygen bar.
Is it because of the induction that you're doing with the CO2 and the water?
Yeah.
Because it wouldn't be induced with the oxygen, right?
Okay, yeah, you have less induction because in this context, right, these guys are both oxygen, right? So they have equal pull, exactly equal pull. Okay, so but between your oxygen and your carbon, you have unequal pull,
It's gonna
right?
shift.
So it's going to shift better, right? And in this case, this is going to give you better shifting, where this guy isn't going to give you better shifting. Does that make sense?
Yeah.
Say this is going to give you enough time to stay in solution, where this one is going to happen so fast because these guys are equal in terms of their pull, right? Exactly equal. Where here you have the difference between this carbon and oxygen, and then you have the difference between this carbon and oxygen. So does that make sense? Okay. 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 Okay, so let's see, let's see. Okay, so now because of this, because of these forces are going to play a part in sorry, I have too many things that are trying to open up. Let's see, do you guys see this slideshow yet?
Oh, it's just the whiteboard.
Okay, so because of these forces, right?
There you
So
go.
these forces are going to sit there and give us the properties of our gases in a sense, and also of our liquids and our solids. So when we're talking about dry ice, so why is it that dry ice sublimes? Why doesn't it go into the liquid form? It goes straight into the gaseous form. Why is that? Where water goes from a liquid, a solid form to a gas form, I mean, a solid form to a liquid form to a gas form.
Is it the forces?
Okay, good answer. It's the forces. You guys are getting good here. When in doubt, just say it's the forces. Intra or intermolecular forces. Which ones?
You should just give extra credit to everyone, Dr. Henry, Cassie, Selena, and I heard Matt and Abby.
Okay, so, but what forces particularly in this case? In the case of water, compared to that of carbon dioxide?
Is it the intra? I'm not too sure.
What is the difference between intra and inter?
Is intra between the two molecules, and then enters like within the molecule, like within one molecule?
Intra, stands for like, I'm thinking all about me, you know, intra. So that's only one molecule in that molecule itself. In inter, like interstate, is between molecules.
Oh, it's flipped, right?
That's right.
Oh, okay.
Okay. So now let's get to the specific intermolecular forces. Which ones are involved? Which ones are involved with carbon dioxide? Just because it's all pure carbon dioxide. Pure carbon dioxide, which ones are going to be involved? Come on, you had a definition of them all. Take a gamble. Come on, somebody roll some dice. Alberto, what do you think? So we're saying the question is, which forces are involved from going from a solid of carbon dioxide to a liquid?
Would it be the dispersion force?
That's right. So we were only going to have dispersion forces when we're talking about CO2. Okay, so those are the only ones that are going to be involved. It's going to just be that induced dipole, right? Or dispersion. That's what it's also called. Okay, now water, what about water? Going from ice to liquid. Kayla,
Not really sure, to be honest.
take a gamble.
The dipole.
It's not quite dipole. It's a little stronger than dipole. And you're right, it's dipole. Technically, it's dipole, but it's a special case of dipole. What did I say was a special case of dipole?
Induced.
Not induced. Induced is not a special case of dipole.
I don't know.
Which ones have we said? Give me my options. Maybe you'll help somebody else help you. So which? Tell me from the strongest to the weakest. What are my forces?
There's ion.
Okay. So is it an ion?
I don't think so.
No, because do you have a total positive charge and a total negative charge interacting together?
No.
Case of
Alright.
H2O? Nope. Okay, so we know it's not that one, so we eliminated that one. Okay, what is the next one?
I don't know. I didn't write it down.
Okay, who's going to tell her the next one?
Ion dipole.
We have ion dipole, right? So then that's something that is charged and something that is not charged. Well, these are both water molecules, right? Two water molecules or multiple water molecules interacting with each other. Are any of them totally positive and totally negative?
No.
Nope. So we can't, that's not that one either. Okay. Then the next one.
Hydrogen.
Hydrogen. Oh, hydrogen. Oh, that's interesting. So what is the rule about hydrogen?
You have to have oxygen, nitrogen, or fluorine.
You have to have oxygen, nitrogen, fluorine, and hydrogen, right?
Yeah.
So does this
Well-
have oxygen, nitrogen, fluorine, and hydrogen?
Yes.
Ooh, guess what it's gonna be?
Hydrogen.
Hydrogen, right? So we know that hydrogen bonds are stronger, right? And it makes sense. So since hydrogen bonds are stronger, we get a liquid forming rather than just going straight from a gas. So dispersionary forces are weak, right? It doesn't take much energy to sit there and break them. Just blowing on it essentially will break it, right? And isn't that what happens when we blow on dry ice?
Don't you get the vapor?
You get vapor, right? So it immediately sublimes because those are weak interactions. It takes little energy to sit there and disrupt them. Us blowing on it was enough energy to sit there and disrupt it. Does that make sense? Where water, what happens if you blow on water? Anything happening?
No.
Right? Nothing happens, right? Is there enough energy for me to sit there and cause it to go from water to steam? What do I have to do to get it to go from water to steam?
Heat.
I need to put some heat into it, right? If I sit it outside long enough, it'll do it on a hot day, right? Because there's enough heat going into the system to start disrupting those interactions. Does that make sense?
Yeah.
Okay,
Yeah.
good. Okay, so to disrupt those interactions, it's gonna require energy. And we can't get away from energy, right? We've been talking about energy. Okay, so we're gonna either need kinetic energy, which is adding heat to systems causes the molecules to speed up, that gets that kinetic energy, right? So in that case, but we're not gonna disrupt the intramolecular forces, right? We're not gonna be breaking those bonds because we don't have enough energy to disrupt those bonds. All we have enough energy to do is to go from one phase to the other phase, right?
Can we
So,
slow down for just one quick second?
sure.
Can we talk about the hydrogen bond really quick? You said it has to have oxygen, hydrogen, nitrogen, or what else?
Or fluorine.
Okay.
So
Really
you have to have
tough one.
hydrogen. Hydrogen has to be there, and you have to have it interacting with either a oxygen, a fluorine, or a nitrogen. Because those are your three strongest electronegative molecules.
Okay.
Okay. Okay, so if we go from that solid, right? We increase the kinetic energy, it goes to a liquid. And then it goes from a liquid to a gas. Does that make sense?
Does kinetic energy only affect the intermolecular? Is that right? You said it doesn't have an effect on the intra.
That's right. There's not
Okay.
enough energy. So, well, kinetic energy can, if we put enough in there, it could have an effect. But,
Okay.
you know, but at the level that we're doing it, like we boil something, right? We don't change. Water doesn't become, all of a sudden becomes, it doesn't become oxygen gas and hydrogen gas. It becomes steam. Still water, still H2O, but it's
Right.
just steam, right?
Okay. So, but you have to have a lot of kinetic energy to do the intramolecular.
That's right. It takes
Okay.
a lot of energy to break bonds,
Okay.
to break covalent bonds, yeah. Okay. So here is an example. We have condensation, right? Condensation. And then here we have the vapors that are above water. Okay. So you guys with me so far? Nobody jumped off a bridge yet? Okay. So what happens in the case of you guys see? There you go. Okay, so we've talked about the different types of IMF, the intermolecular forces. We talked about the hydrogen bond, we talked about dipole, we've talked about dispersionary forces. We've also explained to you the other names. So these are some examples, right? So here, this guy is a dipole. And it's considered to be a dipole because in this case, even though we have hydrogen, this guy, this interaction here is not with one of the strong guys, it's with a chlorine. So chlorine isn't as strong as the other guys. It's close, but it isn't as strong. And so this guy still is going to be partially positive, and this guy's going to be partially negative. And because of that, you're going to get this interaction. So this is your intra or intermolecular, where this represents, that bond represents your intramolecular. Okay.
Chlorine is negative, not positive, right?
Sorry. Yeah, I got carried away.
Okay, I was just making sure.
Good answer. Good job. And so then on this molecule, this negative is going to be interacting with the positive, and then that's going to represent our intermolecular forces. Okay. And we know, as I said, this guy is a lot easier to break than this guy. So that bond, that actual sharing of electrons is a very strong, it's strong. It's that intramolecular forces are very strong, where intermolecular forces are weak. Okay. Does that make sense? The bond between the actual molecule. So it takes a lot of energy to sit there and disrupt.
Yeah, it makes sense. Well, to me it does.
Okay. So all substances are going to have dispersionary forces, your polar substances and your nonpolar substances, but primarily your nonpolar substances. Your nonpolar substances are going to have to use the induced dipole to sit there and interact. Okay, and that process is a temporary process, right? It's not a permanent. It's where you're actually just shifting between the two. So these are temporary dipoles. It's that shifting. Okay, does this kind of make it a little bit clear?
Yeah.
Okay, so we have to understand that polarization, right? That polarization is going to be an essential part of it. Okay, so when we're talking about our diatomic molecules, right? In the case of our diatomic molecules, so these are fluorine, chlorine, bromine. So these guys are going to have equal sharing, right? And so they're going to be non-polar molecules. So what is going to be the force that's going to be involved in this process?
You said the dispersion, and that, but then you said they're going to have to go through the induction.
Yes. So, well, dispersion is that induced dipole, you know, so that's what dispersion is. That's just another name. So, but if you take a look at this, right? So the energy that it takes to sit there and get these guys to say melt, right? So it melts at 53 K. Okay, so that basically means it goes from solid to liquid at 53 K. 53 K is how many degrees Celsius?
Negative 220.
So it's negative 220 degrees Celsius, right? So we know that that is really, really cold. Because we know that 0 degrees is freezing. So anything that's below 273, right, is below freezing. So all of these guys are all below freezing, okay? So that basically means you have to put a lot of energy to sit there and get this guy to melt. Yes, no, maybe?
Yeah.
No, there's
You
not
said
going to
it's
be a
going
lot
to
of
take a
energy.
lot of energy. That was
I
it
asked you
wouldn't.
if it would take a lot of energy. No, it wouldn't take a lot of energy.
No.
Oh.
Okay,
More
so it's
heat
not,
would be.
yeah, or heat. Yeah, exactly. It's not going to take a lot of heat to sit there and get them to sit there and melt. And so the thing is, so this is that point. So a lot of these guys are gases at room temperature because they're non-polar, right? So there's nothing really sticking it together. Water is polar. So at room temperature, what is water? Water. Oh. Okay, I know it's not that hard. Let me rephrase the question. What is water at room temperature? Is it a solid, liquid, or gas?
Liquid.
Liquid.
Okay, it's a liquid, right? Where all of these guys at room temperature, these guys here, all of these guys at room temperature are gases because of their intermolecular forces. Does that make sense? Okay.
Yes.
Okay, so I'm going to stop here since we're over time. And then we'll pick this up and finish it on Wednesday.
Okay.
Okay.
Sounds good.
Okay. But are you guys picking it up? Is it not? Are you struggling? Or is it good?
No, I'll figure it out. I just need to look over the chapter as well. That helps
Okay.
too.
Okay. Okay, with that, peace. I'll see you guys on Thursday. You guys on Friday, I'll have your exams
Wednesday.
ready for you. Wednesday. And your next exam will be, your next exam will be the 23rd.
Why?
Because I love you guys.
I'm gonna be so crying.
No, you'll be fine because it's all the stuff that you guys did the last week before spring break, you know, and I know you guys know it like the back of your hands. And the stuff that you guys did in the lab, right? So you guys are going to be like, I got this. And then it's also going to be this stuff.